Modified machine, we'll call it M1. So, as usual, stage numbers, and the first line is a description of the input string to the Turing machine. Well, it's just some string X, right? Just any old string X. Okay, so this machine M1, first thing it does, it checks to see if X is equal to W. W is this one. That particular string, that one string that goes in here, whatever it is. Okay, so it checks that the input to M1, if it's W. If it's not, reject, and if it's equal, well then you allow this X, because now you know it is W. You allow it to go into machine M. Okay. And then M will decide accept or reject W. Okay? Now, and so your machine M1 will accept if M accepts W. And let's see, accept, and that's it. So M1 will accept if M accepts. All right. Okay, now just a couple of comments here from Sipser. Let's see what's he saying. So machine M1 obviously has to have information of what W is. Okay, now that information you extract from here. So this Turing machine, this larger Turing machine S will extract this W and supply machine M1 with this information. That's sort of common sense, right? Okay. And so M1, tests whether X equals W in the obvious way. You're just testing two strings, are they equal or not? We did that as an exercise some stage in the past. Okay, so it's all pretty obvious. Okay, so more comment on the theorem now. So we use proof by contradiction. We assume the existence of a Turing machine R that does decide this. That's the opposite of what we're trying to prove. Okay, and so then we construct a large machine S, as saying before, that uses R. And so here's now the formal description of the large machine S. Okay, so again, the first line is usually a description of the input string to the Turing machine. Well, in this case, it's an encoded description of two things. Just some, any old Turing machine W, and any old string M. Okay, so it's encoded. So this machine S can extract the information about these two things. Okay. Right, now machine S now, having extracted the information of M and W, it then constructs machine M1. And we needed this modified machine M1 to get round the problem we had mentioned in the previous proof idea on the previous session, last board. All right. Okay, now you've got R, and S can call on R to run R as a Turing machine with the input is now M1, and because this is the modified M1 is the modified M, and we modified it in such a way to get around that problem. By filtering out all possible strings except W, then we know that if a string did get through, it had to be W, and it was that solved the problem. Right. Okay. So now R decides, right? Okay. So if R accepts, then have S reject. Now why is that? Now why is that? Why do we do the opposite? Why does S do the opposite of R? Common sense says what? So if R accepts, if R accepts, what is R doing? If R accepts, that means this machine generates the empty set. Okay. And we want S, what do we want S to do? We want S to decide. It's getting tougher, right? You really have to put on your thinking caps. Now, the really bright ones over you will probably see it immediately. The rest of us, we have to think harder, right, step by step. Now, if R accepts this, what does that mean? It means that this machine blocks all strings. But M1 blocks all strings anyway. So it also blocks, W. It blocks W. It blocks this W here. Okay? So it blocks W. Now we want that W to be accepted. So if that accepts, we do the opposite, reject. Yeah, I think that's the answer. Okay, and hence the other way around. So if R rejects, what does that mean? Well, that means that this machine here does generate at least one string. And because it's M1, that one string that it generates is W. Okay? So we want our S to accept that W. So we make it accept. Well, a general comment, right? We're in chapter 5, and chapter 6 is tougher. So we're now well into first year master's level. This is master's level of abstraction and thinking, and you have to get it line by line. It's non-trivial, as I tend to say. All right. Now a couple of notes again by Sipser. Again, it's sort of common sense. So your larger Turing machine S, it has to be able to compute a description of this, because it needs it to put it into here, right? So it needs to be able to compute a description of that from the description of M and W. So that's sort of obvious, and then he says that S, the larger Turing machine, can do that because why? Well, it only needs to add a few extra states to M, okay? That do this test, that do the, because that's the sort of the essence, that testing with the input X is equal to W. That's the essence of the modification from M to M1. Okay, and it only needs a finite number of states, he says. Okay, all right. Now the essence of the proof. Okay, so if R is a decider for that, then we come to the conclusion that our S here either rejects or accepts. So that means it holds. So that means that S is a decider. Okay, so S, that Turing machine S, decides the language ATM, and that's a no-no because we know ATM is undecidable, right? And therefore, from the reasoning saying before, therefore we know that ETM must be undecidable because we reduced the problem of deciding ATM to the problem of deciding E, TM. We know the first one, the first problem A, well, we know that that problem is undecidable. Therefore, on the right hand side, the problem on the right hand side, deciding whether this is, is this language decidable? We know that therefore this is undecidable. Okay, so there's that proof. Okay. Right. Now we get on to another problem of this kind. We'll show another language will prove that it is undecidable. So I can start. I can introduce what the problem is. I won't get very far because at the end of the session. So another, well, putting it here in terms of computational problem, and you can translate that, as always, into a corresponding language problem, right, a la Sipser. So the problem is, can a given Turing machine, can it recognize a language that a simpler machine, for example a finite automaton, can recognize? So let me reword that. Say you have a finite automaton and it recognizes a certain language. Okay. Well, therefore that language, by definition, is a regular language. Right? That's what a regular language is. That's how you define it. It's a language that is recognized by a finite automaton. Right? Okay. So just how to actually specify the problem. What do you start with? I'll wait till next session.